Hello, it's Keith here, and this is lesson 1 of the Hello World series of my SuperH assembly programming tutorials. We're looking at the Sega Saturn today, and what we're going to do is we're going to create a single ASM file which will show the Hello World example here on an emulator. We're using this emulator here, and this is a binary file we've created which is simpler than a CD, so basically it's an executable that this emulator can run. We're going to set up the screen, we're going to show the text to the screen. I'm using my own font, and so we're plotting that font to the screen as a bitmap. So that's what we're going to look at today. We're also going to look at the assembler I'm using and how to compile it from the command line. So hopefully this will get you started if you want to assemble, and you can use my build scripts. You can go to the website, download them, and you can hopefully get things running straight away. But if you want to make things yourself, then because this is a single ASM file, hopefully it'll be easier for you to port to a different system, because that's something that I find very hard when I'm just getting started. You've got these multiple files, you just want to show something on the screen, and you're having to pick apart various macros and things and try and convert them for your assembler. Not fun. So we don't do that. We just use a single file, and we use hopefully something that's easy to convert. So this is the ASM file we're looking at today. That's what you just saw running. So the first thing we need to do is we need to start our assembly at the right memory location for the bin file, and it's this memory address here, 6004000. That's the destination that we need to start our code at as a binary file. As I say, it's not a true CD file, but it's enough for some testing. Now, what we've got to do first is we've got to turn our screen on and get it set up. The screen is using VDP2. There's two video display pieces of hardware in the Sega Saturn. We're using the second one, which is good for bitmap screens and things like that. So its base of its registers are at this memory address here. And so we're going to use various ones as offsets from that. You can see we're basically changing our 11 to move to the various ones, and I've documented the various ones and their purposes here in the comments. So again, if you're trying to port this and you want to change the way it works, hopefully that'll help you out. So basically what we need to do is we need to set up the minimal settings for the screen. So it's setting up our screen layout here and the VRAM banking. So we're using 5-bit per channel. We will see that as we set up our palette later. The screen is being set up with a width of 512 in the VRAM, but that's not actually all visible. I think it's 320 pixels wide that are visible, something like that. So you can't see it all. But the actual logical area is 512 bytes wide, and we are setting up as a 256 colors. So we got each byte is a color number, and our palette defines the actual RGB component, and we'll see that in just a moment. So here we're setting up the VRAM layout here, and then what we're doing here is we're setting up the offsets for the scrolling, and we're setting up the map area here. Now what we're then got to do is we are setting up the colors here. So we're setting up our colors layout here, and we're setting up as a bitmap screen, as I say, 1 byte per color pixel, so 1 byte per pixel here, nice and easy to work with. We're then setting up our screen, enabling the screen layer and turning on the screen here. So as I say, all of these are just some settings for VDP2 that we kind of need to use as is to get the screen set up for our purposes. Okay, so our screen's set up and switched on now, but it's not ready to draw anything because we need to set up some colors. Now, this is the destination address for the VDP2 color RAM. So we're going to stream a sequence of bytes, 16-bit values effectively, to this. So what we're doing is we're moving a 16-bit value one at a time here, repeating for the 4 palette entries. I've only set up 4 colors, that's all this example needs. So actually only needs 2 to be honest, but I tend to set up the original 4 that the old Amstrad CPC used to use. So that's why we have blue, yellow, and red and cyan, I believe those are. So basically the format in 16 bits here is there's 1 unused bit, there's 5 bits for blue, 5 bits for green, and 5 bits for red. So if you want to change the colors, you should be able to do so pretty easily by changing those. And obviously if you want to add more colors, you can do so and just change the number that are being read in. While we're down here, we'll just discuss the other things we've got here. LTORG is relating to the processor. Whenever we define a large literal value here online, for example this is too large to be contained within a single command, so the assembler actually puts that at LTORG and puts a reference to that as an offset. We're not going to go into the assembly in details here because I've got a tutorial on the SuperH2 assembly if you need to know what the commands all do, but just being as we're there, I thought I'd mention that. Here's the string we're going to show to the screen, hello world. Ends with a 255 character. I always use 255 in my tutorials rather than 0, but you can change it to 0 if you prefer, should be pretty easy. Here's the font, and again, this is actually the same font as I've used in all my tutorials. It's 1 bit per pixel, and it's an 8 by 8 pixel font. That means that one line of our font is 1 byte, and there's 8 bytes per character, and that's important later. The font also has no character below space. Space is character 32, and that's important later as well. Now, so that's our font, that's our text that we're trying to show, and that's our palette that we're going to set up. But we also need some variables that we're going to use for our cursor. The way I do my tutorials is I create a print char routine, and then I build on that for the other functions. So what this does is just print a single character to the screen, and it has a sort of cursor position, so that if you print a character, the next character print will appear one across the screen. So we need some memory to store that X and Y position. So I've defined a user RAM with 8 longs in it, and I'm using 2 of those longs for cursor X and cursor Y. Those are offsets within that user RAM, and you'll see those used later on. Okay. So we set up our palette here. We're just reading in bytes from the palette address here, 16-bit values, sorry, and we are doing that, and we're doing that 4 times to get the 4 colors set up. What we're then going to do here is we are loading the address of user RAM into R14, and we're basically writing a 0 to both the X and Y position as offsets within that user RAM, the R14 pointing to user RAM there. Now, what we're then going to do is we're going to show our hello world text to the screen. We load the address of that into R13 here, and then we run this print string subroutine here, and that print string subroutine we'll see in a moment. The last thing our program does is it simply drops into an infinite loop, so it just halts the processor basically. Just lets us see what's going on. So that's the end of this program. Now the print string routine, very straightforward. So all we're doing here is, you can see we're storing the return register here into SP. That's because we're running subroutines and we're storing that return register here. So that's the return address. We need to do that if we're nesting subroutines. We are loading a single byte from our string here into R0, and we're comparing it to 255. We're actually comparing it to -1 because that's a sign extended value of 255, basically all the bits at F there. So we are comparing at 32 bits here. That's why we're doing that. We're moving the byte here, it's being sign extended, and we're comparing to that sign extended value there. So that's comparing to -1. You could change that to 0 if you wanted to end your strings in 0 though. Now at the end we return, but if we get anything else, we run the print char subroutine, and we just repeat until we get to the end of our string. So all of the dirty work today is being done by print char. It's doing a lot of work, so it's quite long, but it's quite functional. The way I work whenever I'm trying to program a new system is I always get something on the screen, a pixel. That would be good if we can get the screen switched on and we can get data onto that screen. We're already halfway there. Then I do print char. I get a character on the screen. I use that to print hello world, and then I extend that and I create some debugging tools. I show the contents of registers. I show contents of the memory and things, and that allows me to learn to program the system and also the processor. But all of that requires print char, which is what we're looking at. So this is really, once I've got a character to the screen, I'm usually fine with everything because you've got all the control you need and all of the output you need to work out what's going on. Now, the print char routine, because I use it to build up everything else, I back up every single register that it changes. So we're backing up the multiplication registers and R0 to R6 here. Now, this doesn't call any subroutines, so we don't need to back up the return like we did here. So it's self-contained, but we do need to back up those ones. So the first thing we're going to do is we're going to work out the source data from our font. So we're loading the address of our font here. We're subtracting 32 from the character we've been asked to draw. The character is in R0, so we've got no characters below base. If we had a full font that had a character 0 in it, then we wouldn't do that, but our font does do that. It has upper and lower case though, so we don't need to do any case conversion. We're then effectively, we're shifting to the left by 3 bits, and that's effectively multiplying the character number by 8, because as I said, there's 8 bytes per character in our font. It's 1 bit per pixel font. So that's calculating the offset here within the font of the character we want to show. So we know our source bitmap data. We now need to calculate our VRAM destination. Now this is the base of our VRAM, 25E, and then that's 5 zeros, I think that is. So it's a rather long VRAM destination there, but that's our destination address for the top left corner of the screen. What we need to do though is now calculate the offset for our cursor position. So we're taking our cursor X here, and we're effectively multiplying it by 8 here, and that's because there are 8 pixels per character, and each pixel uses a single byte, because as I say, we're using a 255 color screen, and so any value we write to a byte will appear as a pixel on the screen. Very nice and easy to work with. So we're multiplying it by 8 there, and we're adding that as an offset to our 6, and that's moving us basically across the screen to the pixel position that our character should draw. We're then going to do the same for the Y position. So we're taking the Y position as a character here, and we're then multiplying it by 8. So we now have it as a line. Each of our lines is 512 bytes wide. As I say, the screen isn't actually, the visible screen isn't actually quite that wide, but that's the setting that we've used there because of the options we used up here. There are other options here, but we are using the 512 by 256, I think it is we're using. We're using the 512 pixel widescreen, so that's why we're loading 512 into R1 here. And then we're using multiplication, and we're basically saying, YPOS in lines times 512, and so that's what we're doing there. The multiplication command stores the multiplication result in MacL. We move that to R0 and then add that to R6. So we added the X offset here, we're adding the Y offset here. So R6 now contains the top left corner of the destination in VRAM. Now, one slight snag with that is we actually are going to work from right to left. So we shift bits out of our font, and that will be the rightmost bit within our line of a character. And then we draw them to the screen and we work left with each bit that we shift out. So that's what we're going to do. So we're adding 7 here to move to the right hand side of the character, the line of the character that we're about to draw. We've got 8 lines that we want to draw. We're using R1 to do that. We've got 8 pixels that we want to draw per line. We're using R0 to do that. And we've got a loop here. So this is doing one line here across the screen. And then what we're doing here is we are moving a byte out of our source font into R3, and we're incrementing by 1 that source font in R5 there. So that's got a byte in R3. Okay, now R2 is going to remember the pixel that we're going to draw to the screen, potentially. So we're loading the value 1, which is the yellow color, into R2 here, and then we're shifting a bit out of R3, shifting it out to the right-hand side, and then that is setting the T flag. And so if that is a 1, we're going to skip the next command here. So we would skip this command, and the command is loading the value 0 into R2, which is the blue background. So 1 is the yellow foreground, 0 is the blue background, and we're choosing one of those two colors based on the bit that we shifted out of R3. Now, of course, if you wanted a different color, you could change this value or this value here. You could certainly do that if you wanted to have colored fonts. You could change the color each line of your font as well. You do whatever you want. So that's something you can play with maybe. So once we've decided our color, we are writing it as a byte to the screen here in R6. We are moving left, so we're subtracting 1 from R6. So we're going left across the screen here as we are shifting the bits out of our font. We're then going to repeat for the next pixel on this line. Once we've done a line, we're adding 512 to R6, our VRAM destination, but we are adding 8 so that we move to the far right again because we've moved left and we want to end up back on the right-hand side of our character. So we're adding 8 there, and we're then repeating for our next Y line. So we're doing 8 pixels across, 8 lines down. Once we've done that, we've done our character. Very good. So the last thing we want to do is we want to move the X position across 1 for next time. So we are basically getting the current X position here, adding 1 and writing that back again. So that's moved us across the screen by 1. Now there's no wrap when you get to the end of the screen, so you would want to do something else. I have a new line routine. I use most of my code, so we'll see that in just a moment. But so that's the end. We're now drawing our character to the screen and we're ready to draw again. So all we do is we restore all of the registers that we've done anything with during this code, and then we return. So as I say, this print char routine doesn't change any registers at all, and that's quite important. So there's our ASM file that will show the hello world to the screen, but how do we actually get it assembled? Well, I use a batch file. I have my notepad set up with MPP exec, and if I press F6, I can run these batch files, and they automatically include the current running program and the current ASM file and things like that. Now, the batch files themselves, as I say, you're welcome to use mine as is, but if you want to make your own or start from scratch, we'll just discuss quickly what I'm doing. So I'm using ASW, that's a free assembler. It does lots of systems, but it does the SuperH too. Now, the first thing here you can see is %build_find%. This is actually the ASM source file, so if you were just doing this yourself from the command line, that would be hello world.asm or whatever. We've then got the CPU we're specifying. That is the SuperH2. That is the technical name for the SuperH. So that is what we're specifying there, what we're actually assembling. This next thing, -L and O list, and then this file here, all of this is specifying to output the assembly results to a listing file. Now, you don't actually need this if you're making your own. This is a debugging thing, so you can omit it. But if you're trying to learn what the assembler is doing and if you're having trouble, it can really help you out. It will show if the assembler has actually, what assumptions the assembler's made. Sometimes they do optimizations you didn't think they would, and you can see them. And also, if you're having trouble with symbols and labels not working the way you'd expect, sometimes you can see what values the labels are being given. Sometimes the two-pass execution, that you think the label should have a value, but it's actually got a value of 0 at the point you used it, just depending on the assembler and things. So can really help you out. Worth having if you can have it. Now, I'm using multi-platform code that assembles on multiple systems, and I use conditional assembly for that. And so I define a symbol on the command line. Build sat is a symbol that's defined here, and then I have if def build sat in my code and if def 32x, and so switching on and off different parts. But you don't actually need to do that in your examples if you are not doing that kind of thing. And then finally, I'm specifying the output file, and that is prog.build, and that is not the final version of the code. That is just the intermediary stage that we need to finally finish off as a binary file. Fortunately, that finishing off is very easy. We just use p2bin. We specify our intermediary file and our final file, prog.bin here. That is converting it to a final binary file, and that is exactly what we gave it to assemble. Is now been created as binary data. So if we need any headers and things, we would need to include them into ourselves, but we don't in this case. Then so the final thing I'm doing is I'm using this emulator here, which I have no idea how to pronounce. I don't know how that's supposed to be pronounced. Yabaus or something like that. I don't know. Anyway, it's good. It's good emulator. So we can't pronounce it, but we can use it. And so we're specifying the source binary file we want to run here, and we are specifying a BIOS file here. So that is starting up the emulator and running our example. Now, you're welcome to use my build scripts and my my things, but if you're going your own, I would strongly suggest you spend a little time in the early days figuring out your build environment and working out what the fastest way to get from test code to running example is. If you spend half a day doing that and you end up having to debug your code and run it thousands and thousands of times, you'll save that time in the long run. So it's definitely worth trying to get everything running in the shortest amount of time possible. And as I say, for me, the shortest amount of time possible is I press F6 and hit enter, and then a few moments later, there's our example. So that's what I think you should be trying to aim for if possible. If it's not, then it's not. But if it's possible, you will really appreciate that when you're tearing your hair out trying to get your code working because there's a bug in it, you can't find it because you'll be assembling dozens and dozens of times if you're anything like me. Now, that is the most minimal example. There's no include files in that, so there's only the bitmap font file. That's the only separate thing. What I do always provide with these is my more advanced example, which we won't go into the full code of because it's complicated, but you can have it as a sort of bonus, and this is what I would suggest you sort of look at using if you are looking to start off on your own and you just want something to get you started. What this is it's an extension of the Hello World, and it has a register dump and also a memory dump, and so these are my monitor tools as I call them. So basically, we can use these very simply. We have a subroutine called monitor, and that shouldn't change any of the registers. And we have memdump, which will show part of the memory. And I use these for testing. If I want to learn how to read the joystick, for example, I write my code that's hopefully reading the joystick, and then I show the contents of the register to the screen, and I can see my up, down, left, and right changing the registers. And if it's not working right, maybe I need to dump part of the memory to figure out what's going wrong. Well, I use that memdump routine to do that as well. So these are my go-to, and that's what, as I say, once you've got that print char routine, everything else is easy. All I've done is I've added another command that the monitor mem.need is a new line command, so that resets the X position, adds one to the Y position. That's all it does. Very simple addition there, just a needed routine by that subroutine. And then the last thing that it does need is it needs a basic macros ASM file. So as I say, an additional ASM file. Also, the monitor is a separate ASM. As I say, I try and do a single file for the minimal example, but that's too much for the more complex ones. So basic macros really only has two macros, a push all and a pop all, and these are just some simple routines I use to quickly back up and restore all the registers for if I'm doing general things in a subroutine and I want to be quick and I don't want to work out exactly which registers I'm working with. I use those, and those are used by the monitor to back up and restore all the registers. So there we go. As I say, go to my website, download the source code, the build scripts, and you're welcome to have a go with them, do anything you want with them. And if you use parts of these in some amazing commercial project and you make $100 billion, good luck to you. You don't need to give me credit or anything, or you're welcome to use them in anything you can. So do that. And as I say, if you're interested in my tutorials, check out my SuperH tutorials. I've got tutorials on all kinds of other systems as well. And please stick around, like and subscribe and follow on, because we are going to be doing the 32X next time. And I've got a few other of these really simple single ASM file examples coming later for the Saturn as well. I've got some joystick and bitmap drawing examples. So please stick around for those. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching. Goodbye.